And for the rest of the class, welcome. It's 2:30 now, so let's get started. Reading the syllabus, I see that we have an exam a week from today, and that will be over the material since our last exam. The format will be the same format we used on the last exam, and it will be timed. We'll use the class period, and you can have the whole class period. I'll make up that exam probably tomorrow morning. And once I get it made up, I'll send you a list similar to what I did the last time. It'll tell you a little bit more specifically where the questions will come from on the exam. As before, you can use your textbook and your notes while you take the exam. And that's the only references you can use. Everything else is expected to be your own work. So I'm ready to do some more statistics. The last time we met, we talked about estimating a proportion, and we're going to review that a little bit. And then we're going to talk about estimating some other statistics that actually we're estimating population parameters that were called upon, required to estimate on a fairly regular basis. So let's get started. I'm going to put my screen up so that we can write some math here. So we'll just, I think today, start out with an example. What proportion call it P, of Texans smoke? So if we ask that question, more than likely you'd have no idea, and neither would I. I would have no idea what proportion of Texans smoke. I know that some smoke and some don't smoke. And I think probably a lot less smoke than did 10 years ago, but I don't know what that proportion is. I know that it's a number that would exist, but how would I find it? Well, it would probably be as a proportion. It'd probably be really hard to impossible to find exactly, but it maybe wouldn't be too hard to estimate. Now, there are two ways that we talked about estimating that proportion, or any proportion. On Tuesday, we talked about a point estimate. And we get a point estimate by taking a sample of some size. Well, let's just suppose that we took a sample, say 250 persons. That gives me an N of 250. And why don't we let X equal the number of smokers in the sample, and suppose X was equal to 39, then our point estimate is going to be P hat, which I'd call the sample proportion, which would be X over N. X is the number of smokers in the sample, N is the sample size. And in this case, this would be a 39 over 250 equals 0.156. So my point estimate for a symbol, we would call it p hat, and it's equal to 0.156. And so then I may say to you, I would say, my point estimate is that a little over 15.5% of Texans are smoking cigarettes. I hope that's adult Texans. In fact, the question didn't say cigarettes, did it? It just said smoke. So a little over 15.5% are smoking. That's my point estimate. That's a little less than I'd like, and it's a little less than I can easily do, because I'm saying close to 15.5%, but I'm not telling you how close I think that is. And I'm not telling you what kind of confidence I have in that estimate. So better would be a 1 minus alpha confidence interval estimate of P. I'm going to put that in parentheses again, because P is sometimes probability, and I want to keep it clear, this is proportion in this context. So better would be a 1 minus alpha confidence interval for P. And we found out on Tuesday that interval would be P hat plus and minus E, where E is called the margin of error statisticians kind of tend to call that the maximum error of the estimate, but the two mean exactly the same thing. Pollsters usually talk about the margin of error, and you see this in the news a lot, so I'm going to use margin of error. And E has a relatively simple definition. It's a critical value under the Z curve, Z alpha by 2. Now this alpha is related to the confidence. The confidence is 1 minus alpha, and this alpha is related, can be calculated from the confidence. So the margin of error is Z alpha by 2, and then P hat Q hat over N, and then we need to take the square root. So that's the margin of error. Now, if we can calculate P hat X over N and E, then we can easily calculate the 1 minus alpha confidence interval. And the whole thing is not difficult to do. Let's just do it and see how unhard it is. Unhard is a brand new word I just made up. So 1 minus alpha is given in this problem as, I think I gave it a value early in the problem. Oh, I didn't, but let's give it a value right now. Let's call it a 98% confidence interval. So let's make it 0.98. 98% confidence interval. Then alpha would be 0.02, and alpha by 2 would be 0.01. Now what we need is Z alpha by 2. So I'm going to sketch this again. I think the sketch helps to keep us from making mistakes. So this would be Z alpha by 2 is a point on the horizontal axis under a Z curve. So we'll just kind of sketch out a Z curve, and maybe look kind of like that. And I know from work we've done in the last month that Z alpha by 2 would be a point right about here. Now alpha by 2 in this particular instance would be an 0.1. You see we calculated that. And the location of that is such that it cuts an area of 0.1 in the upper tail. And this would be a Z curve, of course. Now, if it cuts an area of 0.1 in the upper tail, it cuts an area of 99, which of course I mean 0.99 in the lower tail. And that would be a key to easily finding what this number is. I guess there's not much reason not to just, we've done this so many times, but we can do it again. We'll calculate with Minitab a probability distribution. Now we want a Z distribution, which is a kind of normal distribution. And we know the area, and so we want, this is going to be an inverse cumulative probability. So we've checked the right radio button. It's a Z, so the mean would be 0 and the standard deviation 1. Those are all okay. Inverse cumulative means that our input constant is going to be the area to the left of the boundary point that we're asking Minitab to find. And the to the right of the boundary point, as I recall, was 0.1. So the left, it's just a matter of me remembering what we wrote down a second ago. To the left is 0.99. So I need to put a 0.99 in for the input constant and double check normal distribution with 0, 1. So that's a Z distribution. Inverse cumulative probability radio button, that's correct. Input constant is the area to the left of the point we want to find. Looks like everything's okay. And Minitab tells us that it's a 2.32635. What I'm going to do is just use 2 decimal digits. So make that a 2.33, rounding to 2 decimal digits. Let's go back to our picture. And Minitab has just told us that this point right here, which we name Z.01 because it cuts an area of 0.1 under a Z curve in the upper tail, and that point is 2.33. 2.33. So there's the Z alpha by 2. Now we need the P hat and the Q hat. Well, P hat we computed a while ago. It's up here. I'll scroll back up so you can see it again. P hat is the sample proportion. It's 39 over 250 is a 0.156. So P hat is 0.156. And Q hat is the complement. So subtract from 1.156 and you get an 844. Don't trust me on that. If I add these two, I should get 1. 6 and 4 is 10, so there's a 1 to carry. 5 and 4 is 9, and 1 to carry is 10. 1 and 8 is 9, and the 1 to carry is 10. So if I add these, I'd get 1.000. That just tells me I've got these right. I wasn't really terribly concerned about that to begin with. I was pretty sure I had it right. So let's see now, do we have everything we need to compute E? Z alpha by 2, we found that. P hat, we found that. Q hat, we found that. N was our sample size, that was 250. I think we've got everything. We're going to have to do the arithmetic, but E is going to be 2.33 and then times the square root of 156, the decimal point goes right there, and 844, decimal point goes there, and that's over, the sample size was 250, and we take the square root of that whole thing, and that's equal to, well, there's nothing in here that we wouldn't just do with the calculator. So assuming that we've got our calculator out, we punch in all those numbers and it's 0.0535. So I know already, I'll go ahead and pronounce it. I know that the margin of error is going to be right at 5% here. It's 0.0535. It's 5 and 35/100%. That's the margin of error. We wanted to find the confidence interval. We haven't quite done that yet, but the confidence interval is going to be p hat minus e up to p hat plus e, like that. So my confidence interval is going to be 0.156 minus 0.0535, comma, 0.156 plus 0.0535. And then do that arithmetic, and I'll go ahead and do the arithmetic first. 0.102, 0.210 is a 98% confidence interval. For P, proportion of smokers in Texas. Now, a statistician would probably report the confidence interval to you just like that. A pollster might say P is, maybe would say approximately 15.6% plus or minus 5%, rounding the 5.3, that is the 0.0535, the margin of error, 0.0535, rounding that to 5%. That's, they say the same thing, but that's basically, that's what the pollster would tell you. Note that, use our Latin again, note bono, if the confidence interval is left, comma, right, then right minus left by 2 would be the margin of error. So if we gave you the confidence interval and the confidence, we're not hiding the margin of error from you. The width of the confidence interval is 2 times the margin of error. And what's right always? What's right in the middle of the confidence interval? Our point estimate. You see, it's P plus and minus E. So you go 1E down, 1E up. That makes the width 2E. And what's right in the middle? P hat, which is our point estimate. And that's how you find a confidence interval for a proportion. Now, again, as review, we've got 3 components here. We've got 1 minus alpha, which is the confidence. We've got the margin of error, which we call E, and we've got the sample size, which we call N. But these are not in isolation. They depend upon and play off of each other. So if you're required to come up with an estimate of something, estimate of anything, and if you're required to have high confidence, that is 1 minus alpha is close to 100, and to have a small margin of error, E is small, then be prepared, N is going to have to be large. Now, what's the downside of that? Well, the downside of that is very often there'd be considerable expense to taking a really big sample. But you can't have big 1 minus alpha, big confidence, small margin of error without having a big sample size. Now, we did a problem the last time we met where we calculated for a given 1 minus alpha and E, how big the sample would be. We might look at that just one more time. We did it this way. We said, well, the margin of error is equal to Z alpha by 2 P hat Q hat over N. This is just repeating something we already know. And if I'm asking you about the sample size, then I want you to solve for N. So let's see if we can solve this little equation for N. Again, we did this a few days ago, but we can do it again. It won't hurt to do it again. I'm going to note that this is equal to E Z alpha by 2, no change there. The numerator is going to be P hat Q hat under the radical, and the denominator is going to be the square root of N. That's an algebraically equivalent rewrite of this piece right here. The square root of a ratio is the ratio of the square roots. The reason I did that is because it's N that I'm after. So I'd like to break out the term with the N in it and get it by itself. Now, what would I do? Well, I want to get the N over here by itself, and I want to get the E over on the right-hand side. In high school, and I notice that many of you still kind of rely on doing this, you'd say, well, let's see, I want to multiply both sides by square root N divided by E. And if I do that there, I got to do it over here, square root N divided by E. Now, why do you do that? Well, because here the E's are going to cancel out, and I'll have the square root of N. That's all that I've got on the left-hand side. And here the square root of N's are going to cancel out. And so I've got, going from here down to here, I've got the square root of N is equal to Z alpha by 2 P hat Q hat under the radical sign, and that's over E. And then the last thing I do, because I don't want to know about the square root of N, I want to know about N. So I'd square both sides. And if I do that, I get an N is equal to, and I could write it this way. Nice thing about algebra, and the bad thing about algebra is it gives us always multiple ways to do anything we're doing. Square those, and then say P hat Q hat. Now, personally, I don't think that we need to publish a separate way to calculate N. If I can remember the definition of E, I can always calculate N. But there's one of those kind of off green sheets in your textbook where the author just does this and presents N to you as a formula. And it's this one exactly. It's exactly this. If you want to mark that page, it's certainly convenient not to have to go through these manipulations. So mark that page, and you can always just refer to it if you need to find N for a given kind of situation. Let's suppose we've got our formula right here, so I'll leave that on there. So we want to estimate now, P can be anything. We want to estimate P with, I just picked these numbers to illustrate, 95% confidence, and 5% margin of error. What is P? Well, I mean, it doesn't matter. P could be the proportion of poisonous snakes that we find in Texas. Out of all the snakes in Texas, what proportion are poisonous? Or it could be the proportion of voters that will vote in favor of improving the parks, a bond issue to improve the parks, or it could be the proportion of people that are currently are COVID positive. I mean, it can be just anything. It doesn't matter. That doesn't change the math here. So we want to estimate P with 95% confidence and 5% margin of error. How big must N be? How big is N? And here's the formula that we worked out. So we would say that N is going to have to be a couple things we need to figure out here. So we'll get to them. Got a parentheses that look like that I got a square. Now the thing down here is E, that's my margin of error. So that's a 0.05 since we want a 5% margin of error. And P hat, Q hat, well, we don't know them yet. And actually we're saying, well, how big does N have to be in order to satisfy these conditions? That tells me we haven't sampled yet. If I'd sampled already, I'd know what N was. I want to know how big N has to be. So I don't know P hat, Q hat. There are a couple things that occur to me here. One would be if there's been a similar study in recent years that we have a lot of confidence in, we might use their value of P hat. We might use the value they came up with for the estimate of whatever proportion we're looking for. And that would kind of give us a starting place. That's not a bad idea if we have some value of P hat that we've got some faith in. That's one way to do that. Another way that people often do is to say, well, okay, I know I'm going to need kind of a big sample here, but just to kick this off, let's do a pilot study, and we'll just look at 100 people. We'll just sample 100 people, and we'll find the sample proportion from that 100, and that'll be the value that I'll use right here for P hat while I'm calculating N. So I could take this from a pilot study. And the third thing that I can do is to let P hat and Q hat be 1/2. And I would call that the conservative thing to do. And it's conservative in the sense that this will lead to an N that I guarantee will be as big as I need. In fact, it'll probably be a little bit bigger than I really need. But it would be better to have N bigger than to have it too small. If it's too small, I can't have 95% confidence with 5% margin of error. So if I use 1/2 for P hat, Q hat, I will wind up probably with more confidence than 95% and less margin of error than 5%. That's the good kind of outcome. But now the downside of that is N is going to be bigger than we absolutely need, but it's still the conservative way to proceed. So let's proceed conservatively like that. Now there's one chunk left off, and that's this Z alpha by 2. And at this time, I hope that is purely mechanical for you. We've got a Z curve, and the Z curve looks something like that, and we'll put a Z on it for a label. And Z alpha by 2, now what would alpha by 2 mean? Well, 1 minus alpha is 0.95. You could do this in your head, I think. Alpha is 0.05, just subtracting. Alpha by 2 is equal to 0.025, half of 0.05. And so Z alpha by 2 would be Z 0.025, meaning the area up here would be 0.025. And so the area down here would be 975. And we'd go to Minitab, and we would calculate probability distributions. It would be the inverse because I know the area, I'm looking for the boundary. And when I did that, and it's equal to 1.96. So given a Z curve, 1.96 cuts off 0.25 in the upper tail, hence 975 in the lower tail. That means that Z 0.25 is 1.96. What goes here in this blank spot? Z alpha by 2, and alpha by 2 is 0.25. This is 1.96. So we got all the pieces. Now we just get out the calculator. And when we get out the calculator, this will turn out to be 384.16. But of course, we can't sample 1/16 of a brake pad or a snake or a human being. And so if we're solving for n, we use the ceiling function, which gives us 185. The ceiling function just says round up. So again, that's in the conservative direction. This will make n maybe a little bit bigger than what I need, but I know I'll be able to get 95% confidence with a 5% or less margin of error if I take n as big as, and I don't know why there was a 3 there, 385 people or whatever objects it is we're dealing with in this example. So that is solving for n. And again, the big three are not isolated. The confidence, the margin of error, and the sample size influence each other. And I cannot simultaneously optimize all three. Without going through a lot of mathematics that past experience tells me you probably don't want to see, I will say recall at some level that Z is part of computing confidence interval for P, and it shows up in a natural way, and thus a Z alpha by 2 is used, and you know where it's used. You multiply Z alpha by 2 to get E. You multiply Z alpha by 2 times P hat Q hat over N, and then a square root. Actually, let me remark right now that it turns out that this square root is the standard deviation of the statistic P hat. This is the standard deviation of P hat. What a coincidence that is. This, just remember that if you can. This is the standard deviation of P hat. This is a Z alpha by 2. Remember also, because we computed X bar before, the sample mean, if I would take X bar and subtract the population mean and divide by the population standard deviation over the square root of the sample size, now that's something we haven't done in a while, but we have done that before, then this will give me, remember X bar is a random variable. If I compute X bar a bunch of times, I get a bunch of different answers, and it has a probability distribution. And the central limit theorem tells me that the distribution of X bar is going to be normal with a mean mu and a standard deviation like I've written down here in the diameter. So that's an all remember because we've done all that. If I take a normal random variable, subtract its mean, divide by its standard deviation, I get a Z. Now, it's going to turn out in just a second that I want to take a value of X bar and subtract its mean, and I want to divide by the standard deviation of X, that divided by the square root of the sample size, but I don't know this. I need this. I need this one. but I don't know this little piece right here. Well, kind of a sensible thing to do would be to calculate the sample standard deviation, which we called S, and substitute the sample standard deviation for sigma, the population standard deviation. So, you know, X bar would be an estimate of mu, S would be an estimate of sigma, P hat would be an estimate of P. This section of the book is called estimation. So we know how to take a lot of estimates. This would be an estimate of this thing right here. That's a sensible thing to do. But very often sensible things have prices we have to pay. And the price is this statistic is no longer distributed Z. This statistic now has got a brand new name, and it's called a T statistic. Sometimes that's should be written as students possessive, students T. And it's called students T because that's the name that a researcher whose name was William Gossett gave to this distribution. William Gossett was a researcher, a statistician, and biologist working with the Guinness Brewing Company in Dublin, Ireland. And Guinness was trying to improve its product, which was beers and ales. I mean, I only can see one head and one person, but I would say who enjoys Guinness Stout? Thomas, do you like Guinness Stout?
I'm not a big fan of it.
To me, it's too strong. I don't like it, but
too strong for me.
Yeah, that's probably the brew that Guinness Brewery is most famous for. Of course, their other very, very famous thing is the Guinness Book of World Records, which they compiled to settle bar bets. More people you get in having camaraderie and drinking Guinness beer, the better off for them, right? So anyway, William Gossett was a researcher for the Dublin Brewery, the Guinness Brewery, and he was a legitimate statistician. Now, this was a century back, but he wanted to publish his work in academic journals. And so he sought permission of his employer, and Guinness said, we don't have any trouble with you publishing your work in academic journals, but we don't want you to use your name because your name is connected to our brewery. And if other breweries see what you're working on statistically, they may get a clue as to what we're doing with our brews. It may be giving away some trade secrets. Anyway, there's a small chance of that. So William Gossett now has to come up with a name to publish under. And so he just called himself a student of statistics and used the name student for all his academic publications. And that's why we call this distribution students T. And Gossett realized that by estimating this value, estimating the population standard deviation with S, he no longer had a Z distribution, he now had a T distribution. And Gossett knew full well what it looked like. And what it looks like is this. Students' T distribution is centered on 0, and it has a shape that looks like well, this should be over here. I'll take just a second to see. This is always going to be a terrible drawing. But I'll have Minitab draw us a better one in just a second. This is something like what students T look like. Now, a couple other things to remember. Normal distributions have two parameters. If I just say it's a normal distribution, that doesn't tell you enough because that doesn't tell you where it's located back and forth. I've got to tell you the mean to tell you where to drop that normal distribution. And if I don't tell you the standard deviation, you don't know if it's scrunched up or spread out. So to uniquely identify a normal distribution, I've got to give you the mean and the standard deviation. Well, to uniquely identify a t-distribution, because there's a whole family of those also, I've got to give you a parameter. And that parameter is degrees of freedom, which we abbreviate DF. And for students T, the degrees of freedom is the sample size less 1. Now, this t-distribution has a single parameter, and its mean is always 0. It's always going to be shaped like this with a high point right above 0. How this is different from a normal distribution is it's fatter in the tails. Now, under any probability distribution curve, the area is 1. So if t is going to be fatter in the tails, it's got to be shorter in the hump. If I was to put a normal distribution, a z distribution, because the z is centered at 0, if I was to put a z distribution on the same axes, the z distribution, this is an exaggeration a little bit, would look more like that. That would be a z distribution. Now, how are they different? Well, they're different because the z distribution is skinny out here in the tails. It asymptotically approaches the horizontal axis much faster than the t distribution. If the z is skinnier in the tail, since the total area is 1, it's got to be taller in the center, and it will be. I can say that about the t this way. If the t is going to be fatter in the tails, then it's got to be shorter in the center, because the total area is 1. If you put more area out here in the tails, then you've got less area to put here in the center. Now, this is my crumb bum drawing, but let's let Minitab do us a better one. Before we do that, let's note that t with degrees of freedom greater than or equal to 30 looks very, this is all capitals, very much like Z. Now, it isn't a Z, but it looks very much like a Z. Now, let's go to Minitab and see if Minitab will draw some pictures for us that'll convince us of what I've just said. We're going to go to graph, probability distributions. Is this icon right here, which says graph 2 distributions on the same axes. That's what we want to do right now. So we'll select that and say, okay. Now, a dialog box, I want to graph 2 distributions, and so I'm going to have to name those distributions. So this is a pull down, and boy, I've got a bunch of choices here. I could do a beta, a binomial, a Cauchy, a chi-square. I'm going to skip over those and look down here, there's a t. So one of the distributions I want to draw is a t distribution. Now, Minitab doesn't know which t I mean until I tell it a number of degrees of freedom. That will uniquely identify the t distribution we're talking about. And let's just start out by saying 5 degrees of freedom. And the second distribution, I want that to be a normal. Now, again, there's an infinite number of normal distributions. Which one am I talking about? I'm talking about the Z. So it's a normal with a mean of 0, got it, and a standard deviation of 1, got that too. So we could pretty this up with titles and things like that, but I think everything that we need, we filled in. So we'll say, okay. And here's the picture. And this is the same picture I drew you, except it's a whole lot better looking. So the red dashed is the T and the solid blue is the Z. Now, do they look like I said? Well, see the red, it's fatter out here in the tails. Now, how do you pay for that? We put more of the area out in the tails, and so the center piece is not as tall. So when the center, Z is taller than T, in the tails, T is taller than Z. Now, this is a T for 5 degrees of freedom. I don't know why Minitab used a capital T here, because we always use lowercase t for students' T distribution, but that's a capital T. It's okay. It doesn't confuse me. I know it's there, so I can live with it. Let's do this again, but let's increase the number of degrees of freedom. Now kind of gauge how much gap we've got here and how much gap we've got here. I don't think I can put 2 of these up at once. I think that's a feature I'd like to see them add to Minitab, but we can go to graph, probability distribution plot, 2 distributions, say okay. Now this is almost perfectly filled out for what we want. The first distribution is going to be a T, and the second is going to be a normal 0, 1, or a Z. The degrees of freedom, I don't want it to be 5 anymore. I want it to be 15. And when I say okay, I get a plot. And notice how there's not much difference here because the red line has moved up. Why did it move up? Because in the tails, it moved down. So altogether, the red is closer to the blue. And if I get up as far as 30 degrees of freedom, with my eyeball, I probably won't be able to tell the difference between a Z and a T. But still, there is a difference. And the correct distribution to use, if I'm estimating the population standard deviation, the correct distribution is the T distribution. Now, a few years back, when we didn't have technology helping us out all the time, if our sample size was 30 or more, we just use a Z, knowing that was a little bit incorrect, but the amount of incorrectness didn't throw us off. It wasn't enough to matter. But there's no reason to do that now. If the situation calls for a T distribution, use a T, because it's as easy to compute using Minitab or a graphing calculator. It's as easy to compute as Z. So what do I mean by compute? What in the world would we want to compute with a T distribution? So that introduces the next topic. We needed this as background, but what I want you to do now, I want that to hold still, and I want to estimate the average price of a house in Austin. Well, this is sort of a similar and sort of a different problem. We've been estimating, that's the similar part, but we've been estimating proportions, and now I don't want a proportion. I want to know about the average price of a house in Austin. Houses in Austin would be my population, and the average price of those houses would be the population parameter mu. So what I'm really asking here is for you to please estimate mu, the population parameter. So I'll ask the question, what's the average price of a house in Austin? That's what we want to know about. Chances are nobody knows that. You may have heard, prices are going up. They're out of sight in Austin. It's growing faster than US average prices, but what is it? I don't remember. And so what am I going to do? Well, I'm going to do what we always do in statistics. We're going to take a sample and we're going to compute. I want to estimate the population mean. I can't compute that directly because I don't know all prices of houses in Austin, but I can compute the sample mean, which is X bar, and I will I haven't used the word guess in a long time. And I will guess that X bar is close to mu. That seems a very, very reasonable thing to do. X bar is a point estimate. It's a point estimate of mu. And in fact, it's the best point estimate of mu. But the problem with a point estimate, and we've noticed the same problems when we were talking about proportion, the problem with a point estimate is close is undefined. We think that X bar is close to mu, but we don't know how close. We're not putting a bet on that. And we don't know what our confidence is in X bar being close to mu. So I'd like to fix those two things. Well, better is a 1 minus alpha confidence interval estimate of mu. Boy, this language seems very similar to what we did for proportions. And of course, that's not an accident. It is very similar. It's a very similar process. So we want a 1 minus alpha confidence interval estimate of mu. Now, I think I'm just going to jump in and give it to you. We'll call this a turns out. It turns out that the 1 minus alpha confidence interval estimate is X bar plus and minus E, where E is a little bit different. It's still called the margin of error, but it's a little bit different. E is going to be T alpha by 2 S over the square root of n. E is a little bit different, but it's a little bit similar too. Remember this, for a proportion, this turned out to be a Z alpha by 2. Now it's a T alpha by 2, but it's still a critical point in the upper tail of the distribution. And when we were doing proportions, this was P hat Q hat over N under the square root, and that was the standard deviation of P hat. Well, S over the square root of N is an estimate of the standard deviation of X bar. Remember, the central limit theorem says that the standard deviation of X bar would be sigma over the square root of N. But we don't know sigma, so we're substituting S. So that's an estimate of the standard deviation of X bar. So very similar. And I hope similar makes it easier to remember. But you know, computationally, there's nothing very hard about calculating a 1 minus alpha confidence interval for the population mean, because X bar is easy. I take my sample and calculate the sample mean. And E, here's the definition. Well, I've got Minitab to help me find a critical point, T alpha by 2. And I've got data. That's how I calculated X bar. From my data, I can calculate S, and N is my sample size. You know, I think nothing hard here. Let's just review just a little bit more before we go further. We take our sample. We agree on some size N, and our sample looks like then X1, X2, and keep going to Xn. And from formulas we learned first week of class, X bar is equal to sigma Xi over N, which means what? It means you add all these up and divide by how many you had. And S, again, second week of class, we learned that we can calculate that as n times sigma x squared minus sigma, I wouldn't write this down again, but you can if you want to, x squared, and that's all over n times n minus 1, and then we have to take the square root of that. So if I've taken a sample of size n, at least in theory, X bar and S are immediately available to me. I just get out my calculator and I grind through it. Of course, if my X1, X2, X3 are already in Minitab, then it's real easy. I just say, give me the standard deviation, give me the mean. And so there may be some tedium with data entry, but certainly conceptually, there's no problem with calculating S and X bar. And why are we calculating S? Why are we using an estimate here? Why don't we just use the population standard deviation? Well, I mean, think about that. What are we doing? We're estimating the population mean. That's a confession of our ignorance. We don't know the average value of houses in San Antonio. I think we said Austin. If I don't know the average, how likely is it I know the standard deviation? I mean, the chances are 0 that I would know the standard deviation, or near 0 anyway. Maybe some weird case where an angel came and told me what the standard deviation was, but in any rational world, if I don't know X bar, I'm not going to know S. I'm going to have to compute it. All right, so anyway, given all of those reasons, let's get out some data and see if we can calculate the average price house in Austin, an estimate of that, and a confidence interval for it. So let's suppose that we take a sample. I'm going to write down the question. What is mu average house price in Austin? Well, we're going to take a sample, and I just decided last night I'm going to take a sample of size 40. And so I took that sample, and my data was X1, X2 through X40. And then I computed X bar from that sample, and X bar turned out to be 526,241. And from that sample, I computed S. Here's the formula for it. Or I could use technology to help me. And I found that S was 150,000. So I'll go ahead and put in commas here and comma here. And so looking at my formula here for E, I see that I'm going to need a T alpha by 2, where alpha will be tied to the confidence. So I guess we'll make a note here first off. Note, point estimate is X bar equals $526,241. But we want, let's say we want a 90% confidence interval estimate of mu. And a reminder, because I scrolled it off the paper, that's going to be X bar plus and minus E, where E is going to be T alpha by 2 S over the square root of n. So we've got a little bit of computation to do here. I know that 1 minus alpha is equal to 0.90. How do I know that? Because the confidence is 1 minus alpha. So there's the confidence. So I know that alpha is equal to 0.1, and alpha by 2 would be 0.05. And so let's do our sketch. So I've got a T curve. Now, which T is that? All T's are centered on 0, but some T's are fatter in the tails and some are skinnier. Which T is that? This is going to be T with the degrees of freedom equal to, go back to the sample size. The sample size is 40. So for T, the degrees of freedom is going to be 1 less, 39 degrees of freedom. And the value we want right here, the T alpha by 2, well, I'm going to say sort of as always, the T alpha by 2 is what? Is 0.5 this time. See, we computed alpha by 2, it's 0.5. That's going to be a point on the horizontal axis. I'll make a big dot there. That cuts off an area of 0.5 in the upper tail. So what about in the lower tail? Well, everything that remains, that has to be 0.95. So that's all I need to go to Minitab and to come up with this value. And I do need that value, so let's go get it. What do we need to know? We need to know we're doing a T distribution. We need to know that the area to the left of the point we're looking for is 0.95. And we need to know the T distribution that we're using has got 39 degrees of freedom. So that's all we need. So let's go to calculate probability distributions. Now we're going to use a T. I think this is the first time ever. So what does this look like? Chi-square normal? By gosh. The third thing is an F, and the fourth thing is a T, probability distribution for T. And now we've got a dialog box. And so we're looking for a point on the horizontal axis. And so we're looking for an inverse cumulative probability. Good. The degrees of freedom, that identifies a particular T, that's 39 degrees of freedom. It's an inverse, and so our input constant is going to be the area to the left. And that area to the left was, in this problem, I think we said a 90% confidence. I should write these down. We did. We said 90% confidence, and so alpha by 2 is 0.5, and the area all the way from the boundary all the way to the left is 0.95. So this value is 0.95. It's already in there, so I'll leave that alone. Now let's review. T distribution, 39 degrees of freedom. We're doing the inverse probability because we want to find a point on the horizontal axis. When I'm doing an inverse, my input constant is the area to the left. That would be 0.95 in this case. Looks like we've got everything right. So we'll say, okay, and Minitab says the point that you seek is 1.68488. Now let's just use 2 decimal digits here for the sake of simplicity and mark that as 1.68. The point we want is 1.68. Let's put that in our drawing. This point right here is 1.68. When T is 39 degrees of freedom, this is known as a T05. It cuts an area of 0.5 in the upper tail, and its numeric value is 1.68. Now let's double check here. How are we doing? T alpha by 2 is now known to us. It's 1.68. S, we computed earlier, it's 150,000. N is our sample size, that was 40, and we know how to take the square roots. And so now we can calculate E, change color here. We can calculate E as 1.68150000 over the square root of 40 is equal to, and of course that's a calculator problem, and it will turn out to be 39,845. And in this example, that would be dollars. The margin of error is $40,000. The 90% confidence interval estimate of the population mean is X bar minus E, you wouldn't have to write all this out, comma, X bar plus E, close parentheses, which is 500. Now I'll scroll up so you can see where this came from, but this came from our data, 526,241, $526,241 minus $39,845, comma, that's the low end. The high end would be $526,241 plus $39,845. And when you do that arithmetic, it's 486,000, comma 396 to 566,086. And if you want to, those are dollars. And this is a 90% confidence interval estimate of mu, which means what? Well, it means that I'm 90% confident that if we knew mu, it would fit between these two values. Or a pollster might say that mu is estimated at 526,000, and a pollster would probably say $526,000 and drop the 241 with margin of error $40,000. Or they might say, you hear all of these and they mean exactly the same thing, $526,000 plus or minus $40,000. Usually realtors and pollsters and people like that, if they don't specify the confidence, they usually don't specify it, but it's almost always 95%. It certainly doesn't have to be. And statisticians will use different confidence levels, but usually the published things that the popular press prints are a 95% confidence, even if that's not stated. You can work backwards yourself if they give you enough data, and you can calculate what the confidence would be, but usually it's 95%. Okay, that's a pretty good workout for today. We've got a couple minutes left. Do you have any questions?
So we would use the T for, I guess, I'm just a little fuzzy on when you use the Z graph and the T graph.
Okay, you would, from what we know so far, there's more. We're just touching the surface right now, but we use Z when estimating proportions, P, and we use T when estimating means, mu. And you're going to read your book. And so I was going to hide this from you, but you're going to read your book. So you're going to figure this out anyway. You use T when estimating mu if sigma is unknown. And it would be proper to use Z when estimating mu if sigma is known. The reason I was going to hide that from you is because this never happens. If you don't know mu, you don't know sigma. So this case it just doesn't happen. And if one time in 10,000, if it did happen and you didn't know about it and you used T instead, the difference is small enough it won't matter. But if sigma is unknown, which it almost always is, then the proper statistic to use is T. Now, where does it pop up? It pops up when we're computing E. E is equal to Z alpha by 2 and something, or E is equal to T alpha by 2 times something. So that's where it pops up. Now, how did it get introduced in the first place? Well, I'd be really happy to take you through it sometime one-on-one, but let's say we're estimating mu, and what we want a confidence 1 minus alpha, and we want that to be the probability that left is less than mu is less than right. And then we do, and we don't have time to do it now, Thomas, but we do a bunch of substitutions, not substitutions, but we do a bunch of algebraic manipulations on this statement right here. And we wind up with this thing in the center. Have fun over the weekend. Be safe, whatever you do. Study some, get ready for your exam. Even before I send you out the list, it's going to be things we've covered since the previous exam. So the list doesn't really give you that. It doesn't give you any new information. It just kind of compacts things. Have a good weekend.